So let's continue with Makefile. So we're learning this fancy new language called the Makefile language, where you make a file and it kind of automates the compilation process for you. You say all the little recipe names for all the stuff that you want, and it'll go and it'll build that stuff for you. And it'll also look for rules for, like, if you want really this thing down here, it'll go and look at the ingredients. If it doesn't have those required things, it'll go and look for a rule for making those, and it'll go off and make those too. So that's cool. That's what Makefiles are great at. And just write all the rules of how to build what you want once, and then put it in a file called Makefile, and you're off to the races. All right, so let's do what we were doing. Let's continue. Let's make a real Makefile this time. So we had our searching library, right, from last time with searching.cpp, main.cpp, plus a little header file. But we needed to, the compilation process was, take both of these files, separately compile them to make .o files, object code, main.o and searching.o, and then we want to link them together into our main executable file that I think I called searching last time. It doesn't have to be called main. I guess we'll call it main this time, but we gotta link them together. So that's the third rule. So it kind of looks exactly like this, but with different names. So let's go and make this file now. Where do I want to be? First, I need to copy in those things from last time. Copy lecture 24's CPP files to here, and then also the header file. So there's my searching library. Got my files. And now I want to make a new file called Makefile. So with a capital M. And this is the Makefile language now. We're going to make some rules to make all this stuff work. You can make comments in the Makefile with number signs. This is a Makefile comment. And so remember that every rule that we're about to write, every rule looks like the following. It's got a target, the thing that we want, colon, and then you space separate all the ingredients or requirements for the thing you're trying to build. Ingredient 1, ingredient 2, as many as you need. Then you tab over. So Vim should do this automatically, but like you tab over a bunch of times, or just once. It's like over here, and you give the terminal commands to make the target from the ingredients. As many tabbed over lines as you need. Right? The tab and not spaces though. But your editor should do that automatically. And so let's make a rules. Let's be like, all right, I would like searching.o from searching.cpp. Searching.o is the name of my target. How do I build it? What do I need? First, to make searching.o, I need searching.cpp to exist. And then what do I do in order to make this thing work? I need a, by the way, is that going to be, oh, I see. Never mind. Let me fix this in just a sec. Give me a second. I see the problem. Tab it over a couple times even. There. That's probably better. And then I'm here, and what do? I need to make searching.o from searching.cpp. That's the ingredient. And then what do I do once I have it? I say g++ -c on searching.cpp. So that rule will run and create the .o file from searching.cpp. Okay, does that make sense? That's how we build that one. Then we want to make one for main. We want to make main.o, a rule to make main.o. So main.o is the name of the file I want. That's my target. And it requires main.cpp to exist. And then to build main.o from main.cpp, I use g++ -c again on the CPP file. Okay. That's the rule to make that. And then finally, I need one more rule to link them together. I want one final executable. Let's call it main. So my target is main by itself. And I would like to link together the two object files. And so I need those to both exist, main.o and also searching.o, in any order. And then you say what you want. How do you build main from those two things? Well, you link them. You say G++. You give the two of these files. And then you say -o, what you want the thing to be called. We're going to call it the same name as our target main. Usually the target name is the name of the file you're trying to build. And so that's our makefile. All right? And I can run individual rules like this. So to run a makefile, you say make terminal command. It'll look for the makefile. And then you give the name of the target that you'd like to build. Make target name. So I like make searching.o, for example. That'll run that rule. And it will make searching.o. So isn't that fun? And so there it did. It built searching.o. I could say make main. Or I could say make main.o, finally. Make main.o, name of that rule. Oh, sorry, not main.o, make main.o. It'll run that rule, and then there it went, and it made main.o. And then I can say make main. Isn't that beautiful? And so it's linked together. I have a runnable program again. Any questions about that so far? So the make terminal command will run the rules in your makefile. And let me remove all these things. Remove main.o, remove searching.o, and remove main. Let's see. How do I want to do that? Yeah. So now I have no compiled files. The beauty of makefiles is you can just say make main when nothing has been made. I have no .o files yet. You can just say make main, and look at how it notices. Oh, I need this. I don't have it. I better go make it. So you see it run the searching rule first. It's like, oh, I need that. I don't have that either. So it finds this rule and it runs the make the main.o file rule. So you just say make main, and it will build every ingredient if it knows how. And then it makes the thing that you wanted. So I got everything all together, /main. Isn't that fun? That's beautiful, I think. So that's the power of makefiles. You just say once what you want, and it will figure out the rest for you. It will figure out how to build it optimally. And then also, you don't just have to say make target name. You can just say make by itself, and that will run the first rule in your makefile. So usually, you put the most important one up top, like main, and then you can just say make. And it'll build that for you. And notice that's like it knows it has no work to do. It's like I don't have to change anything. It's just the same as before. Nothing has changed. It's like it's up to date. So it's going to be very efficient too. So let me make a change to one of these files. Let's change main.cpp. Just search for something new. I don't know. Let's pick a file or pick a number. Search for it. Search for 42. So there's a new line I just added to main.cpp. So I've changed main.cpp. Watch when I say make again, or make main, either one. Boop. It notices that main.cpp changed. It's like, oh, I require main.o, but main.cpp has changed, so I will remake just that. It has not touched searching.o. It notices that it does not need to recompile that one, and then it relinks them. So it only does the minimal work to get the final thing built for you. And then you have the new functionality. So makefiles are great. They notice when files change, and they will build things in the most optimal way that saves compilation time. So I think that's everything that I wanted to say. Any questions about makefiles? I will be giving you a makefile in a future lab, and so you're going to have to remember how to use it at least. Alright, but if we're good, let us talk about complexity again, because this again is not something that I really want to test you on. Like I promise that if I test you on any of this stuff, like I'll ask you a super simple question that you can just look up on these slides. But I really just want to get you prepared for CSCI 41, so that's why we're going to talk about this. Alright, there's plenty of nice memes too about it. So let's analyze our searching implementations. Won't that be fun? So let's count all those basic operations that we were talking about before. How many basic operations is linear search? How many basic operations is binary search? Because like why go through the trouble of making binary search if it wasn't significantly better? All right. So let's notice that it is significantly better. So remember what a basic operation is. That's like an assignment statement, an arithmetic operation like a plus, a times, checking a condition like less than, something simple like that. That's one operation as far as the computer is concerned. It runs inside of the CPU at the lowest level, and it's usually about a line of code essentially as a basic operation, as long as that line of code isn't like doing fancy things like looping or calling a function. So yeah, we're going to count the basic operations to tell us in a mathematical way how fast a line of code or how fast a function takes to run. Okay? And usually when we're analyzing things, we have some unknown, like we have the size of a vector that we're searching through, and usually we give the letter n, capital N, to represent how big that was. Like, so I think you can imagine that, like, when you're linear searching, it's a little bit it's faster to linear search through a size 3 vector versus a size 3 million vector. Yeah. So the size comes into play, but it's the same analysis at the end of the day. So yeah, let's remember basic operations. Here's like an example. Int x equals, I don't know, 5 plus 2. How many basic operations is this line? You have the addition of 5 and 2. The computer's got to figure out and make 7, one basic operation. And then it's got to shove that into a variable in memory somewhere. So that's the second basic operation. So that's 2 basic ops. All right? And so we want to figure out, like, what is the number of basic operations for, like, linear search when I give it some arbitrary vector of size n, which may be different, and I'm searching for some value, right? So that's the kind of analysis I'd like to do. And so let's analyze linear search. Here's like a copy of linear search from a past semester. It's the same code, though. It's just, going through the thing, looking for the value that we're trying to search for, and then returning the index where we find it, or -1 if it doesn't find it. So let's count all the basic operations in this code, okay? So first of all, the vector v is of an arbitrary size. So let's remember that. v.size, if I need that anywhere in my calculations, let's call that capital N, just to make it quicker to write. And so let's count basic operations in this code. I'll switch to a color that is visible. And so, all right, going through all these guys, let's count the basic operations. We also have to worry about loops. So, all right, for loop. Initialization, that's an assignment, one basic operation. v.size, that is a method call that gives back a value immediately. That's one basic operation, let's imagine. And then we compare that value to I, two basic operations. I++ is secretly I equals I plus 1. So there's a plus and an assignment in one go. So there's two basic operations for that guy. And we also have to figure out how many times it repeats. And then we do v at I, that goes somewhere in a vector, gets a value back, one basic operation. And then comparing that to another variable, a second basic operation. So two basic operations for the condition of that if statement. Are we following me? Does that make sense? And then potentially we'll return one basic operation, let's say, to return. And then once we jump out of this loop, we might return again, so another basic operation there. Right? So there's all my basic operations, but some are repeated, so we got to worry about that. So let's figure out how many times we're repeating stuff. So our loop initialization, this guy, this I equals 0 thing, that is one basic operation. One op, let's say. And then we need to repeat this loop, the body, how many times? N times, right? So I is going from 0 to n minus 1. That's n times total. So do n times what? We have 1, 2 basic operation, 3, 4, 5, 6, potentially 7. This is just like the worst case. We're only ever going to return once, but 7, let's say, in the worst case for a body. For a run of the body. So let's say that's 7 ops, 7 operations. And then, to stop the loop, we must check the condition one last time. Remember that? That's 2 operations to notice that we're done with the loop. That's an n plus 1th time, right? 2 operations to notice that we're done with the loop. 2 ops. And then potentially we're down here and we're returning if we didn't find it. That's 1 more op. All right, so that's our analysis. Does that make enough sense how we counted those things? And so here's a nice mathematical number that, regardless of your CPU speed, tells us how fast this function is to run. It is apparently 1, 2, 3, 4. 4 operations plus 7 times n. 4 plus 7 times n, 4 plus 7n, and that's our analysis. That's how many operations it takes to run linear search for a size n vector. In like the worst case, maybe. Something like that. Okay. Does that make sense? Any questions about how I analyzed that, came up with that number? Because we're about to do binary search, and that's a harder analysis. So I want to make sure we understand this one. All right, binary search time. Sorry it's so small, but you remember it. Where are we at? Let's start tallying basic operations. We have to initialize these guys. We have, oh gosh, initialize low assignment. Get size, get that back. That's a basic operation. -1, subtraction, and then put in the thing assignment. That's 3 basic operations for that line. Comparing low to high in the loop now, that's 1 basic operation. Plus division, I'll just do it faster now. Go somewhere in the vector, compare the value, the plus, assignment, dot at, comparison, subtraction, assignment, returning, 1 basic operation. And then down here, another basic operation. So that's that.
What about the assignment at line 7?
Oh, did I miss it? Thank you. Oh, thank you. Yeah, perfect. Yeah, so that's another basic operation. When you get to CSCI 41, you will learn that you don't have to be this precise, but it's good that we're noticing all these numbers. You'll never have to do this kind of counting really ever again, but let's do it. So we got these are 4 basic operations at the start there, and then we are looping some arbitrary amount of times. We don't know how many times we're looping yet, so do blank times. We're not sure yet how many times this loop will go in the worst case. Till like figures out we didn't find it or something. Do blank times how many operations though? Every loop. We got comparison. So that's 1. Then we got 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13. It seems like it's 13. That's 13 ops. Repeated some amount of times. We're not sure yet. And then 1 more comparison of the loop to notice that we're done, to potentially break out of the loop in like the worst case where we don't find it. There's another 1. And then finally a return -1 in the worst case. There, something like that. So that's our analysis. All right. Now the question is, how many times will we, in the worst case, because that's what we care about, how bad could this be? How many times would we run this loop? Like if we didn't find the thing, if it wasn't there, and we ended up returning -1 at the end of breaking out of the loop, like that's the worst case possible, how many times would the loop run its body? That's the question of the day. So we have to figure that out. And so we have to ask the question, like, what is the loop doing? Like, when does it stop? It stops when we don't have a search space anymore, right? And so what does that mean? Initially, our search space was a whole darn vector, right? And each time we make a guess and look in the middle, we cut off half the vector, right? Our search space halves. It's cut in half. And so the question is, how many times, in the worst case, how many times could I chop this vector in half and still have a valid search space to look through, and still have a body to go through? Does that make sense? How many times can I chop this in half? Because that'll tell me how many times, in the worst case, the body would run. Look in the middle. Okay, maybe go this way. Okay, maybe go this way. Down and down and down until I have, like, nothing left. How many times can you do that? How many times can you chop a size n thing in half? Because we're saying that the vector is size n again. It's the logarithm. All right, the answer is, how many times can you have a search space, divide by 2, and still have something left in it? Log base 2 of n times. Base 2 because you're chopping in half. It's getting exponentially smaller and smaller, and so that is the inverse of an exponential is a logarithm. Yeah? So it's log base 2 of n times that we will run this body. Maybe log base 2 of n plus 1 or something. Not a big deal. Log base 2 of n is what is governing how many times we run the body. And so that's really the analysis. All right? So this all becomes now, it's 13 times, well, I guess 6 at the front. 6 plus 13 times log base 2 of n. Okay? And so that's our analysis for binary search. Any questions about that? Again, not going to test you on how to do this. That's a CSCI 41 topic, but you're getting ready for it. All right, so we come up with this number for linear search and this number for binary search. What does it mean? All right, let me prove to you that binary search just blows linear search out of the water. It's so much faster. All right, so usually you care about when you have large values for your n, for your vector that you're going through. So like we came up with, it was like 13 log base 2 of n for us. It's always, in the long run, going to end up smaller than anything that has just n out in front. Because like we had 7 n. It's a smaller number out in front of the n, right, for linear search. Binary search has 13 out in front, but it was log base 2 of n that we were multiplying it by. And so that's significantly smaller, okay? So let me show this to you. I think you can imagine that it won't take long for binary search to get much better. Because here's like the graph of how many basic operations. Like here's how n is, n getting bigger this way, large n that way. And then the number of operations for an n looks like this, right? For linear search, it's like the graph of a line. That's why we call it linear search, by the way. It was like 7n plus something. It looked like this. It was a line. Yeah, that was the linear search graph, how much work it will take for a given size vector. And then binary search is the graph of a logarithm, okay, with a constant out in front. So maybe, because the 13 is bigger than the 7, maybe for like tiny vectors, it'll take a little bit more basic operations to do linear search. But we all know that the graph of a logarithm looks like this, and it flattens out kind of. It grows so much more slowly than this kind of thing. All right, so binary search. All right, so this is large n this way, large. And that's what we really care about. All right, so in the end, binary search is always better in the end. It'll even be better in the end if it was a horrible implementation that had like a 1 million out in front of here. The constant was 1 million times log base 2 of n. Even comparing that to like a perfect linear search that had like 1, if we change this to a 1n plus f. Even if it looked like that, even if you had a million out in front of the constant as in front of this log base 2, it will still, for a large n, eventually win. Be much, much faster. Okay? So I hope that makes sense. So just simplifying, pretend you had a size 1 million vector. In the worst case, you'd have to do essentially 1 million times a constant basic operations to linear search that, right? If you're looking for something that's not there. If instead you did binary search, if it was sorted and you had a size 1 million vector, log base 2 of 1 million is, you do like 20 things, 20 basic operations to search through a size 1 million vector with binary search. Okay, do you see how much better that is? So that's why we care, pretty much. I hope that made at least a little bit of sense, but that's our analysis. Any questions about that? It's pretty cool. And actually, because logs just win out in the end compared to like n's versus n squareds are bigger than that, and cubes are bigger than that, we have a certain kind of notation that we like to use in computer science when we're analyzing algorithms. It's called big O notation. Again, not going to test you on this really. This is a CSCI 41 concept, but it's good to have seen once. So here's the rules of like putting an algorithm's analysis into big O notation so that other people can compare it to other things. What you do is we had like, 7n plus 4. You take the highest order term only, and you drop everything else. So that's the first step. So you like chop off the 4, and now you just have 7n. Because I think you can imagine that for giant n, the plus 4 is not really doing much. Yeah, that's what we really care about. And then also, you drop any constants out in front of that highest order term. So we chop off the 7, we just say that this is n. Because like you add one more thing in the body, now it's 8n. Like that didn't really contribute too much. It's not a big deal. So the n is really what we care about here. All right. So that's our analysis. And so we say now that, I guess I got it wrong last semester. It was 7n plus 4. We turn that into, 7n. We turn that into n. And we say linear search is big O of n. That is that's the analysis. That's how you say it. And so big O, it's just like a little shorthand for us to like figure out how fast a function grows, because we're generating a function here, a mathematical function. So this notation was invented by mathematicians for other things, but we stole it as computer scientists because it's useful for us. It just kind of tells us in general how fast a thing grows. So we like to use it for algorithms because we end up coming up with a number that represents a function that represents how fast our function takes, how long it takes for a given input size. That's the idea. That's linear search. And then here's our binary search, 13 plus 4, I guess. Chop off the plus 4. We get 13 log base 2 of n. Chop off the 13 and get log base 2 of n. And so we say binary search is big O of log base 2 of n. And we call that logarithmic time. And we say big O of n is linear time, right? Because the graph looks like a line, and this is a log graph, of course. And so log is significantly faster than linear, no matter what, for large n. And that is what we care about. So that's like, at a glance, we can see like, oh yeah, binary search, if it has this analysis, it's much, much faster than linear search. We'll prefer that if we can run that one, we want that one. Okay, that's the idea. And this is, the whole point of this is so that like we're not like setting a stopwatch and figuring out how long it takes to run linear search, figuring out how long it takes to run binary search. Because every CPU is faster. Like binary search is going to be slower on my laptop compared to your giant tower desktop sitting in front of you. So that's not really useful. But sometimes you do want to use a stopwatch. So here's how you do it. You use the CTime library. Here's one way at least. This will time how long it takes to run something in seconds. So in the CTime library, there is a clock function that you can call. And so if you call it, that like looks at the clock on the wall inside of your CPU. And it's like you can save that, and the type that it returns is a special type called clock t. And so like you look at the clock, look at the time right before you start running your algorithm, and then you run it, and then you look at the clock again. So you just save the start and the end time. And then you subtract the two, convert it to a double so that you can do double division, and then divide by a constant in the library called clocks per second, because apparently a clock has nothing to do with seconds originally. It's like CPU specific. So when you divide by that, it calculates actual seconds elapsed. So one day I might force you to do this, and so that's how you do it with the CTime library. But if we're happy, I just have one last thing I want to talk about. I want to talk about sorting algorithms. Again, this is more of a 41 concept. Honestly, more of like a 4-year college algorithms class concept. But sorting is an important thing. So I want to show it to you. And if I test you on any of it, I promise to have simple questions again. So to set the scene, right, sorting is a very normal algorithm to want to have, right? We would like to be able to sort stuff. So let's say, here's a sample. Let's say I have a bunch of numbers in this order, 18, 23, 12, 8, blah, blah, blah. So pretend I tape, like I have a bunch of papers, like I write 18 on a piece of paper, I write 23 on a piece of paper, and I tape them to the whiteboard in that exact order, like instead of these words, this printed text. This was a piece of paper, this was a piece of paper. I put it in this order. Right? Pretend I did that. How would you sort them, right? Or maybe it was magnetic. How would you like, I would move the 8 over here, the 7 over here, like in the least amount of movings, how would you sort like that string of numbers? How would you do it? So please, you don't have to write this down anywhere, but just discuss with your group, like what would be the algorithm, like if you were to physically have to move those things and you were lazy about it, what would be the algorithm that you use to sort it most efficiently? How would you do it? And I will tell you right now that you're going to come up with one of the two algorithms. Usually, most people come up with either selection sort or insertion sort. There's a name for what's probably in your head right now. So discuss with your group, how would you sort this thing, and then we'll come back and I'll tell you a bunch of sorting algorithms. A few more seconds to discuss. Alright, I hope you got some good ideas out there. Let's come back. Let's talk about some sorting algorithms. Here's the one that I would have in my head. I'd be like, alright, 7 is the smallest thing. Just shove it over there. 8 is the next smallest thing. Shove it over there. Something like that. That's probably what I would do. And that's called selection sort, by the way. There's another one that is very common, like when you're like playing cards or something. Maybe you thought of that one. It's like you just like move them over in a weird way. We'll get to that. But that's how I might do it. Maybe you thought the same. But let me show you a bunch of sorting algorithms. I'm not going to give you like real code. Your book has real code. This is like pseudocode. And I'm going to take us to a cool website too that I'll give you the link to eventually. I guess technically you have it if you go and you look at the last set of slides. But here is a fun little website that has, this is a sample array, all right? And so here are the real numbers in the array. It's very small, 61, 86, 16, blah, blah, blah. So these are the numbers in the array, and then it has these bars that represent like the relative, how large that number is compared to other things in the array. So this is going to be a animation of a bunch of different sorting algorithms, and the goal is to, like, once it's sorted, you're going to see the numbers will be in order, of course, but then the bars will be just gradually and beautifully increasing. That's the goal. All right. So let me teach you the first algorithm. This is the simplest sorting algorithm. It's called bubble sort. It's very cute. We're going to visualize it. And here's the pseudocode for it. It's got a nested loop. It's a doubly nested loop. I'll try to explain it. But all it does is, you've seen this algorithm before. This is swapping. All it does is it swaps things that are out of order that are right next to each other. Numbers j versus j plus 1. If they're out of order, swap them. All right? So in general, like you have a messed up array, 8, 6, 7, 5, 3. The goal of a sorting algorithm is to eventually sort this thing. So we're going to transform this into, what, 3, 5, 6, 7, 8. But the way that we're going to do it depends on the algorithm. All right, so bubble sort will get the job done eventually. It is a very slow algorithm, though. So here's what it would do. 8, 6, 7, 5, 3. What it does is it swaps elements that are out of order that are right next to each other. So what the first thing it's going to do is going to look at these two guys and it's going to compare them. And it's going to be like, is 8 and 6 in order or out of order? They're out of order, so it's going to swap them. It's only going to swap things that are right next to each other. Index j and j plus 1. So it'll make this 6 and it'll make this 8. And then it'll look at these two guys. It's only like zooming in really far and it's looking at things just right next to each other. 8 and 7, it'll say, are those out of order? Yes. So it'll swap them. Now it's 7, 8. So every time you do this, the array gets slightly closer to being sorted, but it's going to take a while. Then it compares 8 and 5. Out of order, so it'll swap them. So it'll do like, this is now 5, this is now 8. Then it'll compare 8 and 3, out of order, so it will swap them. 3, 8. And notice how after one round of going through all the pairs in the array, you place the 8 in the right spot. So the 8 is fine now. It is in the sorted spot. It's never going to need to go anywhere else. So after one round, you're done with that index, so you never have to look at it again. Now you just go and you sort these guys, the rest of these, with a bubble sort way. So that's why there's a nested loop. You have to go through the array, essentially, n minus 1 times, size minus 1 times. Every time you do it, you have a slightly smaller array to work with. So you don't have to ever look at this index again. So it's always up to number size minus I minus 1. That's why it's doing it that way. And then it'll compare these guys. Like, all right, let's do it again. 6 and 7 in order, cool. 7 and 5, ooh, out of order, swap. So now 5 and 7. And then, all right, 7 versus 3, out of order, swap. 3 and 7. This is getting a little bit ugly, sorry. 3, 7. And now, 7's in the right spot. So every time, every round, by the end, like, it's This is in the right spot now, this is in the right spot. So now I'm going to bubble sort. I'm going to try all the pairs for this smaller array, slowly but surely. If everything's out of order, we'll swap them. Right? So that's what the I is doing. It's like it's accounting for the worst case number of times you have to go through the array and swap stuff. And then every round of that outer loop, the next biggest element will always be placed in the right correct position. Then you never have to go there again. So it's always winning out that swapping game. It's always being moved to the right, slowly but surely. Right? And so this is bubble sort. Let me show that to you. Here's a cute little algorithm. You can click randomize to randomize the array, and I'll set the speed to really fast. And then here's bubble sort. It's going to highlight every pair of things as it's working through it, and you'll see it swapping. It's like, ooh, it's swapping things. And you see how the biggest thing is starting to win out and be moved to the right. So you never have to touch this right side of this array anymore. Everything's in the right spot, but it's just swapping stuff that's right next to each other. And so it's going to take a while for this like smallest element, this 2 over here, to get moved to the left. It's going to take quite a while. It's only, it's working at a very, it's very zoomed in right now. Slowly but surely, it's swapping stuff out of order. The right side that is pretty much sorted. These are good, and you never have to look here again. So it slowly but surely has a smaller and smaller array to be sorting. And eventually, with enough swaps of things that are right next to each other, it will end up sorting the entire array. Yay! Pretty. So that's bubble sort. All right. It is, well, you can think about it this way. It's like, all right, swapping, this is about 10 basic operations, give or take. 10 times n times another n, so like n squared. It's big O of n squared. That's the sorting algorithm. It's bubble sort. And this is pretty slow, I think you can imagine. You could have done this a lot better. There's a lot of swaps. It's slow even for n squared. The constant out in front is too big. Silly how many times we're doing stuff. Because, like, it took forever to get that small element way over the left. That's silly. There's better n squared sorting algorithms even. So the next one's called selection sort. And this is maybe the algorithm that you came up with to sort a bunch of papers on the desk or on the whiteboard. So let me show you selection sort. It makes a bit more sense. It's a little complicated to program, but the idea behind it should make a lot of sense to you. What selection sort does is it's like, all right, I'm working on this index, index 0. I'm going to go through the entire array from here onwards and find the thing that needs to go here. It's the smallest thing, right? The smallest thing, the entire array needs to go in that index 0. Yeah. So that's what selection sort does. It's like, all right, for I equals 0, so this is the index I'm trying to fill, give me the smallest thing in the rest of that array. So go and find the 3, and you swap it. You shove it right there. 3, 8. And so now you're done with this. You go through, find the smallest thing, you're done with this. Now the rest of this array, just sort the rest of it. 3's in the right spot. Now work with index 1. Now I is 1, and it's like, all right, go through the rest of the array, find the smallest thing. So let's go through all these guys, find the smallest thing, it'll find the 5. And it'll shove the 5 right there. 5 and 6. And so now, okay, we have an even smaller array. Go and find the smallest thing in here and like put it at the start. So it'll move the 6 back, and I think you get the idea. That's selection sort. It is selecting the minimum each round. It's trying to fill that location. Again, it's an n squared loop. It's doing this n times here, and this is getting smaller each time, but it works out to be about n in the long run. And then notice how many times it's swapping. It's only swapping after it's like found the minimum. So it's not swapping a million times like it was in bubble sort. So the constant out in front, it's still an n squared algorithm, but the constant out in front is much, much smaller. So it's a faster n squared algorithm because there's a lot less swaps. All right, so here is selection sort. It'll highlight its best guess of the minimum, and then it'll put it at the start. So there's highlighting the minimum, put it in there. Now it's done with that index. Filled in that index. So it's slowly but surely finding the minimum, placing it at the start, selecting the minimum. All right. So once you understand the idea, I think you can program it. Given enough time, you understand the algorithm, you can generate the code, the nested loops that this would turn into. I believe in you. And it's almost halfway done. Much, much faster than bubble sort, even though it's also n squared. Hey, there it goes, just finding the minimum, placing it in that spot. It's the minimum of the rest of the array. It's getting smaller each time. So that's selection sort. Any questions about that? Does it make enough sense? This is honestly one of the most intuitive algorithms. Like, this is how I would sort things. Selection sort in real life. Insertion sort is another n-squared algorithm that looks a bit weird. Apparently, like in textbooks, people write like this is how you would sort the hand that you're dealt in when you're playing cards or something. So let me give this as the example. 8, 6, 7, 5, 3. It's completely out of order backwards. Here's my example array for insertion sort. What insertion sort does is instead of being like selection sort and like putting the right thing in index 0 immediately, what it's going to do is it's going to slowly expand its frontier. That's what it's called. And it's going to keep a locally sorted subarray. So like at the beginning, it's like, all right, from index 0 to index 0, that's already sorted. Cool. And then it'll go from index 0 to index 1. It'll bring in this index, bring in the 6, and it'll like, all right, this is the new thing I've added. Let me move it down to where it belongs. So it'll move the 6 left because the 6 is smaller. All right, so it'll look at this sized array, and then, all right, now it's 6 and 8. And so you see how this is not quite sorted when you look at it and you zoom out. Like the 3 needs to really eventually end up in index 0. But for the first 2 elements of the original array, those are now in sorted order. That's what insertion sort does. All right. So now it's going to like, all right, it's going to expand its frontier to go to index 3. And so it's like, all right, I'm going to bring in the 7 into this, and I'm going to move the 7 to where it belongs. So it'll move it down in between the 8 and the 6. So now 7 will go here, 8 will go here. And now you see like the first 3 numbers up to index 2, the first 3 numbers of this original array are in sorted order now. That's the difference between insertion sort and selection sort. For selection sort, like the final answer is in this slot. But for insertion sort, it's like it's only the things that were originally here are now sorted. Right? It's not moving values down to that range of indices until like we've brought them in. So like the 3, it belongs here, but we're not going to get to it until the very last round. So next it'll move in the 5. It'll expand the frontier one last time, move it in the 5 to where it belongs, and it will actually shove it to the start. That's the goal. That's how that will work. So just keep on swapping things, moving it downwards. So this is insertion sort. It's a for loop plus a while loop this time. So like initially the original frontier is size 2, like we're working with index 1, moving it down to where it belongs. And then it's like, while that thing is out of order, and like the thing to the left of it is a bit bigger, let's swap it. Swap those things, keep on moving it downwards. Like advance your frontier, bring in the 5, and keep on swapping it downwards as long as the 5 is smaller than the thing to the left of it. So that's how that works. For loop plus a while loop, so that's n times in the worst case. So it's n squared in the worst case. That's the average case as well. But it's a bit faster. Insertion sort has the best constant out in front of it for an n-squared algorithm. So watch it work. It'll make a locally sorted subarray, moving stuff down if they need to be. So like it is, you see how it's working with this smaller array over here to the left, and it's in sorted order. It's just bringing the next thing down to where it belongs, bringing the next thing down to where it belongs. That's the insertion sort algorithm. These are all algorithms to do the same thing, but they work differently. So it only needs to move down as far as it needs to go, and you can just stop because everything to the left is smaller. Boop, boop. Move it down, move it down, move it down a little bit. That one needs to go pretty far. That one goes about halfway. That one goes about halfway. And then they're all in the right spot. That's insertion sort. Slowly but surely building up a locally sorted subarray until the whole thing is the subarray, and now it's sorted. All right. The beauty of insertion sort is that it has a different best case analysis. If the array is already sorted, it's just going to look to the left, right? Or very close to being sorted. It's just going to look to the thing to the left and see, like, is it in the right spot yet? So if the thing's already sorted, I'll click insertion sort again. It'll just, like, look to the left. Do I need to move this thing down anymore? No. And so it's like, I'm done. Just got to look through the whole array once, which is linear time. So that's insertion sort. It has a linear best case, which is fun. Yeah. This is probably the best n-squared algorithm because of that best case. Yeah. So again, I don't want you to memorize the algorithms. More like understand the process, understand the setup, understand why the diagram or why the animation is working the way it is, because then you could program it yourself. You don't have to memorize lines of code, memorize ideas. All right, I have two other algorithms. I'm not going to code these for you. I'll maybe code them up for you in CSCI 41, but your book has all this if you want to look into it more. The next two algorithms are the faster ones, called merge sort and quick sort, and they're different. They're a bit different, and they're recursive as well. So recursion is power here. So they're also called divide and conquer algorithms. They're they're a special kind of recursive algorithm. All right. So these two next sorting algorithms are called divide and conquer algorithms because they are recursive, and the problems that they generate, like when you're making recursive calls, they split up evenly and they don't overlap. That's what it means to be a divide and conquer algorithm. It's like you're dividing this array in half and conquering both sides of it recursively. So you end up like breaking it down into smaller problems. That's the recursion until they're simple enough. Hit a base case, and then you build up the answer using the results of those smaller problems of equal size that did not overlap. All right, that's a mouthful, but here's like an example. This is a sorting algorithm. Let's say we had 8, 6, 7, 5, 3, 0. Here's merge sort. I'm not going to tell you that yet, but here is an example sorting algorithm that is like, it's called merge sort, and I'll talk about it more on the next slide. But here's your initial array. We're going to divide it and conquer it. So we're going to chop it in half and recursively sort this half. It's a smaller array. You just get to assume the recursion works, and it sorts this half of the array. You get back 6, 7, 8. Yeah? And then, again, you recursively sort the right half of the array, and it's a smaller array, so the recursion guarantees it will be sorted correctly, 0, 3, 5. And then all you have to do, you have these two smaller arrays that are both sorted. You got to, like, shove them back into the original array in sorted order. So, like, you got to play a game of, like, all right, 0 versus 6. Who wins? 0, 0, 3, 5, 6, 7, 8. And so that's fast to do, but that's the algorithm. It's like we divided, we conquered, and then we like bring it back together. So that's an example of a divide and conquer algorithm. That is pretty much in a nutshell what merge sort is. That's the type of recursive sorting algorithm that works exactly like that. All right. It's got a little helper function called merge that does the bring back together thing at the end. But that is exactly what it is. Let me draw it again. 8, 6, 7. That is legitimately what merge sort is. 5, 3, 0. You chop it in half. You recursively sort both halves of that array. Smaller array, so it is guaranteed to work. And then, after you've recursively sorted them, you have two sorted subarrays now, thanks to recursion. And then your job is to merge them back, and there's a helper function called merge that does that. All right. So let's see. What it's got to do is you do need a separate array, so there's some extra space that you have to waste to do merge sort. And then here's the merge algorithm. The merge sort algorithm is everything I've said, and the merge algorithm is like take these two sorted things and bring them together. So you just start off like a pointer or an index variable at the front, because those are the two smaller things, right? The two smallest things in both arrays. And it's like, all right, 0 versus 6, who wins? 0. That's the first index. All right, now 0 versus 3, or 6 versus 3. Who wins now? Who do I place in the next index? Okay, it's the 3. 5 versus 6, 5. All right, now this guy is exhausted, so I'll just take the rest of the other array, 6, 7, 8. That's how that works. That's the merge algorithm. It's very fast once you have two sorted subarrays. So the analysis of this, let me do the analysis in a second. Let me show it to you working. So you're going to watch the recursion happen, and like it's going to draw a helper array down here where it's going to merge them back. But you're going to watch it like section off parts of the array that it's working on right now as far as the recursion is concerned. Like there it goes, working on the left half, merging these two smaller things, merging them back. And so you can see it's kind of gray. It's merging. Now you have a sorted left half, recursively sorting the right half. Scratch work, merging, and then merging the last thing, copying it back in. So I couldn't even explain that, and it was already done. All right. This is a n log n sorting algorithm. So it took, the rest were n squared, so it exchanged a n for a log n. N times log base 2 of n. We know how much faster log base 2 of n is. That's much, much better than n squared. And the reason why, if I can try to explain it, is this is going to recursively chop the array in half. How many times can you chop it in half and still have an array? Log base 2 of n times. And then linear work to do the merging. So that's where the n comes from. That's where the log base 2 of n comes from, if that made any sense. So that's merge sort, much, much faster than the other ones that we've been talking about. All right. The fastest algorithm, it's also n log n, just a better constant out in front. It's called quicksort. There's a lot of words. Read about it in your book. You got a chapter on this. Read about it. It will be fun. But let me draw an example of quicksort. Let's say we've got the array like this: 5, 8, 7, 3, 0. So that's our array. And quicksort works like this. It has a helper, just like merge sort has a helper function called merge. Quicksort has a helper function called partition. And what partition does, you call that first. It picks a special, usually random element of the array, and it calls that its pivot. Let's pretend that we picked a pivot as like index 0. Let's say that 5 is our pivot value. And what it's going to do is going to essentially try to move. It's going to look at the rest of the array, and it's going to try to move everything that is smaller than the pivot to the left side, and try to move everything that's bigger than the pivot to the right side. So just keep on swapping stuff. So it's like it's got the 8 and the 4 now. Those are on the wrong side, right? The 4 needs to be on the left, the 8 needs to be on the right, so we'll swap them. 4 and 8. And then it'll move inwards. Now it's all right, 0 versus 7. Again, the 0 should be on the left because it's smaller than the pivot. The 7 should be on the right. It's bigger than the pivot. So it'll swap them, 0 and 7. And then it's got like 3 and 3, and when those little indices have aligned, that means you're done with that partitioning process. And what we've done is we've chopped off the array in essentially half into things bigger than 5 and to things smaller than 5. And then you can put the 5, you know that where they overlapped, where those indices overlap, that's actually where the 5 really belongs. So you can swap it in there. You can be like, all right, 3, 5. And so now the 5 is in the right spot. You never have to touch the 5 again. And so now you have this sized array and this sized array with big stuff and small stuff that you can recursively quicksort. Okay? That's the goal. All right, so after partitioning, the pivot has the right spot. It knows where it belongs now. And then quicksort works like this. The first thing it does is partition, just like this. Now you got two smaller, like the 5's in the right spot, but you got two smaller subarrays to call quicksort on. So it will recursively make those in the right order, which will then call partition, do weird things all over again. But yeah, once you get two smaller unsorted subarrays like we did, after partitioning, you can call quicksort twice on them to sort them. So you don't actually need any extra space, and so that makes it a bit faster than merge sort. You are kind of at the mercy of your pivot value. If you choose a horrible pivot value where everything is like bigger and nothing is smaller, you haven't chopped the array in half. But usually, if you pick like a random pivot, it will usually chop that each subarray into about half, and so you end up with log base 2 of n number of recursive calls, and so it ends up being n log n again in the average case. So in the worst case, if you pick horrible pivots, it will be n squared if you like chop things off like this, like you big left half, small right half, and you keep doing it like that. It in the worst case becomes n squared, but it's very hard to get it back. All right. Usually we like quicksort because it is the fastest constant out in front of that n log n. So quicksort is one of our faster sorting algorithms. It's the one you generally prefer. So it's quite possible that the sort algorithm in the algorithm library is quicksort. I don't remember who's implementing what, but that is a good potential option here. So let me press quicksort. You'll see it chop the array in half. You'll watch it pick the pivot and start moving things and swapping things. So there's the pivot. The pivot is a line. It's like moving things above the line, pivot value, to the right, and things below it to the left. And then it's recursively sorting those two smaller subarrays, and you see it just highlighting its current stuff that it's worrying about for its recursive calls. Picking a pivot, partitioning, making recursive calls to quick sort again. So it's a little weird, but that's how it works. So it picks a pivot. That was a pretty horrible pivot right now because it's a very big value. And then so it just has a few things on the left, a bunch of things on the right. So usually it about averages out, though, to chop things in half, usually. But yeah, the beauty of quicksort is you don't need any extra space. It'll just go off, keep on recursively calling itself, recursively partitioning, etc., etc. Very, very fast in general. Any questions about any of that? So we've made it to the end. All right. That was a fun little set of slides about a bunch of different stuff. All very algorithmic, I would say. But yeah, that's where I want to leave us today. That is just the lecture for the day. The rest of the time is yours to work on stuff.